Okay, sources of magnetic field. That means how magnetic fields can be produced. How could magnetic fields be produced? Wherever there's an electric current, there is a magnetic field. That's a simple trick, right? If you have an electric current flowing, you're going to have a magnetic field. We're going to look at different shapes of the conductors. Number one, we're going to look at a straight conductor. A straight conductor. Second, we'll look at a circular loop. Third, we'll look at a solenoid. Fourth, if time permits, we'll look at a toroid. So there are four things that we're going to look at. Straight conductor, circular loop or circular coil, solenoid, and toroid. And then for the first time, we'll also define what an ampere is. We've not defined an ampere in the proper way. So that is what this story is about. Now, I want to start this chapter with a magnificent law called the Ampere's law. Because using this, we're going to derive all the equations. That's why the unit of electric current is given in his name. It's such a useful law. What do you need to have here? A straight conductor carrying current. As shown in the diagram, the current is flowing upwards. And we do know that the magnetic field around it is in the form of concentric circles with the center on the conductor. We know that, given by the right-hand grip rule, correct? Now, what you need to do is you imagine as a loop around the conductor. Need not be a circular loop, just a closed path. Can you imagine a closed path around the conductor as I'm trying to build up a closed path, maybe irregular like this? That's a closed path. We can imagine that this path is divided into small segments, as you can see, and I'm considering a small segment of length dl. The current through the conductor is I. Okay, upwards, and according to Ampere's law, the closed integral of B dot dl is equal to mu naught times the current inside the loop. Okay, let's take a look at that again. When you see the symbol, when you see this symbol, that means it's closed. It's a closed integral of the dot product of B and the length of the segment. Now remember, dot product always comes out to cos theta, isn't it? Okay. And that would be equal to mu naught times the current inside that loop. In this example, what's the current inside the loop? It's I, isn't it? Okay. What if it is a circular loop? Now I'm considering exactly a circular path. Remember, that's an imaginary path. Okay? Now I'm considering a circular path of radius r. And if you apply this, what's going to happen? Aren't all the points at equal distance from the conductor? So wouldn't the magnetic field be the same at all those points? Yes. Would be the same, right? Therefore, you can take out B, and then you'll have B integral dl. What's integral dl? Around a circle. Don't say area. Circumference, which is 2 pi r. So B times 2 pi r is equal to mu naught times I. Rearrange, you get B. B is equal to mu naught I by 2 pi r. There you go. So you got the formula for a magnetic field through a straight conductor at a distance r meters from it, carrying a current I amperes. That is done. Exactly what I was trying to tell you, I tried to draw it. It may not be classic diagrams, but that one ought to be classic. Can you explain that? Is that current through the conductor out or in? The second one. I'm talking about this. That current is out of the plane of the board. Now you can surely make out that here the directions are like that, given by the right-hand grip rule, right? Okay, very good. What if the current is flowing into the plane of the board? Then use this. Are you getting what I'm saying now? It must be perfect. So whatever I ask you on this, everybody ought to get it. There's surely going to be one question on the direction of currents and the magnetic fields there. All right, let's move on. Now that takes us to the next topic. There's always going to be a force between two conductors, two parallel conductors. Okay. Consider that you have two conductors, 1 and 2, both carrying currents in the same direction as shown. The currents are I1 and I2. Now here, you have to be very careful. B1 is the magnetic field produced by the current I1 at the conductor 2. B1 is the magnetic field. Does I1 produce a magnetic field? Yes. It produces a magnetic field all around it, right? Okay. So B1 is the magnetic field that is produced by this current I1 at the conductor 2. Can you give me a formula for that? If the distance between, I don't know what I took the distance as, if the distance is D between the conductors, what's the magnetic field? What is the magnetic field at this point due to the current flowing through this one? Is my question. Wouldn't it be mu naught by 2 pi I1 by D? Come on. Mu naught by 2 pi I1 by D. Is that clear enough?
Yes.
What's the direction of that magnetic field? We just finished. What's the direction of that magnetic field at that point? What's the direction of the magnetic field? Into the plane of the board. Right? Okay. Now look at conductor 2. Isn't it also carrying a current? Yes. And when a current carrying conductor is kept in a magnetic field, doesn't a force act on it? What is the formula for force acting on a current carrying conductor kept in a magnetic field? Bill. B times I times the length. Agreed? So now, before we continue further, what will be the force acting on it? Force acting on the second conductor. What's the B? The B is this whole thing, isn't it? So that multiplied by I2 times the length. Right? The length of conductor 2. Okay? And then, questions have to wait. And what will be the direction of that force? How is it given? Remember this rule? You have to hold the right hand first with the fingers in the direction of the current, right? Up. And then when you bend the fingers, it should give the direction of the magnetic field. Is that clear now? Yes, it is. Look, what did you say the direction of the magnetic field is here? You said into the plane of the board. Is the current going up? Yes, it is. So current, magnetic field, what direction is the force acting in? Towards the other conductor. Everybody got that? Yes. Okay. Now, if you think backwards, isn't this current producing a magnetic field here? Yes. What's the direction of that magnetic field? That magnetic field, this current is producing magnetic field at this conductor, right? It will be out of the plane of the board. Okay, and so wouldn't a force act on conductor 1? And what would that direction be? Let's go.
Towards 2.
Conductor, current flowing up, magnetic field out, and the force is going to be... So are these two attracting each other or repelling? Okay, rule. If the currents are flowing the same direction, they attract each other. But if the currents flow in opposite directions, they repel each other. Don't have the time to explain that part, but you can make it out. So two parallel currents attract, anti-parallel currents repel. You know the meaning of anti-parallel, means in opposite directions. So that's what it means. All right, finally, let's get the formula. What is going to be the force between them? Just tell me, will the force exerted by 1 on 2 be the same as the force exerted by 2 on 1? Think. Yes. Definitely the same. And what will the equation be? The strength of the magnetic field, which I'm writing, mu naught by 2 pi, I1 by 2 pi d times I2 times the length. Come on. Isn't it? Okay. Now I'm going to define an ampere. using this idea. What if I1 is equal to I2 and both are equal to 1 ampere? Think, both are 1. And we're considering 1 meter of the conductor. That means the length is 1 meter. And we're also considering that they are kept 1 meter apart. Did you hear me? So I1 is equal to I2 is equal to 1. Distance between them is 1 meter. And we're considering a length of 1 meter. What will you get when you substitute all that into this, somebody? 1? No, you won't get 1. All these became 1, but you still have these two. What's mu naught? What is the value of mu naught? That's what you would get. But mu naught is 4 pi times 10 to the negative 7. 4 pi times 10 to the negative 7. Put it and cancel it. What do you get? So on top you have
2 pi on top. 2.
only 2 on top. Because it's 4 pi by 2 pi. So you would have 2 times 10 to the negative 7 newtons, isn't it? Okay, I'm going to define an ampere. 1 ampere is that current which, when flowing through two parallel conductors kept 1 meter apart in free space, exerts a force of 2 times 10 to the negative 7 newtons per meter of the conductor. Last time. 1 ampere is that current which, when flowing through two conductors kept 1 meter apart in free space, exerts a force of 2 times 10 to the negative 7 Newton per meter of each conductor. That is the definition of an ampere. So defining an ampere, once again, I1 is equal to I2 is equal to 1. 1 ampere, D is 1 meter, and L2 is taken as 1 meter. What you get is the definition of an ampere. Because when you substitute, you get 2 times 10 to the negative 7 Newton per meter. Okay, the forces are attractive. That's what I put up now. Now let's look at the magnetic field of a solenoid. Everybody knows what a solenoid is?
A little motor. A little big motor. You have it like disk drives and things.
Okay, a solenoid is an extended coil. It's a coil that's extended, as you can see in the diagram. Now, what does the diagram represent? What do those dots and crosses show? The solenoid has many turns, and this shows that the current here is coming out and it's going in, right, into the turn. So now you know how the currents are flowing. Is this right? Yes. We're trying to find the magnetic field at the axis of the solenoid. I'm sure you know what axis of the solenoid is. Okay. Now to do that, we consider a particular closed loop. Can you see the particular closed loop we consider here? Look at that. It's rectangular now. That's an imaginary loop. One part of it is outside the solenoid, completely outside, I must say. There are 2 parts here, and there's one part that's completely inside. Are you watching this? If you are, you're going to answer, and it takes 1 minute to get the formula. Like I said, it depends on the understanding. Okay. What do you know about the magnetic field here? This is a point which is far away from the solenoid. Do you think there will be any appreciable magnetic field at that point due to a current flowing through the solenoid? Or do you think it will be negligible? The magnetic field outside a solenoid would be negligible. Therefore, there is no magnetic field here. We're trying to use Ampere's law. What's Ampere's law? B dot dl is equal to mu naught times I. So if B is 0, then the whole thing is 0, isn't it? There is no magnetic field here. Okay. Now let's take these two sides. Be with me. Somebody tell me the direction. You can see the green arrows show the magnetic field. Can you see those? The direction between the magnetic field and this loop, this part of the loop, what's the angle between this part of the loop and the magnetic field? 90. And remember, in Ampere's law, you take dot product which involves a cos, and cos 90 is
0.
so automatically the two sides cancel out. So this part, there's no magnetic field, gone, 0, and these two parts, because the angle is 90 and cos 90 is 0, nothing. Okay, so that leaves us with just this line, isn't it? What's the angle between the magnetic field and the loop? So remember that we are proceeding this way. 0. Cos 0 is maximum. Therefore, if you apply Ampere's law, try to get it on your own. What will you get? Let me also tell you something. Let's say that the length, they've taken it as x, so let's take this as x. Or you label this as L. Instead of x, just call it L. And let's say that the solenoid has, be careful on this one, the solenoid has n turns in 1 meter. This is where students make a mistake. N turns per meter. So how many turns are there in the length L? I said there are n turns in 1 meter. How many turns are there in L meters?
N times L.
Thank you so much. Understanding is key, and I have to take 10 minutes to explain that. N turns in every meter. How many turns in L meters? N times L. How many turns in 2 meters? If there are 10 turns in 1 meter, how many turns in 2 meters? 20. So you multiply, don't you? Okay. So this gives you the total number of turns. You see this relation? The total number of turns is the number of turns in 1 meter multiplied by the length. So when you take that distance, how many turns do you have there? In that length L, how many turns do you have? This is the number of turns, isn't it? Apply Ampere's law, what do you get? Write it and tell me what you get. Tell me what you get. Integral B dot dl is mu naught I. Okay? B is constant taken out. Integral dl is the length. And since you have n turns, caps n turns, you multiply it, you get ni. So take the length to the other side and you got the formula. You got to be very careful about this formula. Once again, I'm trying to tell you that the little n here, what is that? What is the little n? It's the number of turns in 1 meter. If you forget that, you just lose some points for nothing. What's the caps n? Total number of turns in a particular length. So if I give you that there are 1,000 turns in 5 meters, in your formula you're going to use 200. I told you there are 1,000 turns in 5 meters. But in the formula, you're going to use 200. Because 1,000 turns in 5 meters
Can we just leave it
is 200 turns.
and a rail?
You can use either one. But you have to be careful. You have to know what the n stand for. You know what I mean? You have to still know that this is number of turns in 1 meter. This is the total number of turns, total length. Okay, finally, what's the direction of that magnetic field? Well, I know it's shown on the screen to the right side, but how do you get that, is my point.
Well, you have that and you know
You have what?
the currents.
You have the currents. Yeah, because down you can see, you can either use the current coming out or going in, and surely either way you will get the magnetic field to be on the right side. And towards your, what side is this? Your left side. I'm talking, okay. Towards your left side. The magnetic field due to a solenoid perfectly matches the magnetic field due to a bar magnet. Do you know what a bar magnet is? A rectangular magnet? The field of these two are exactly the same. And I think I told you this before. A magnet has 2 poles, isn't it? So the solenoid must have 2 poles. Remember how I told you to find out? When you write the letters S and N, nobody remembers? If you look at the solenoid from this end, you look at it from this end, how is the current flowing? Clockwise or counterclockwise? As you look at the currents in the solenoid from this end, how is it flowing? You see? Imagination. From this end, the current is flowing this way. You see this? this is not how my clock works. This is counterclockwise. If I look at it from the other side, if I look at the current from the other side, now the current flows clockwise. So, how do you remember it? Look at that. Is this clockwise or counterclockwise? Is this clockwise or counterclockwise? I don't know. Go back to.
That's counter.
So if the current appears to be clockwise, that end becomes the south pole. If the current appears to be counterclockwise, that end appears to be the north pole. That's how you find out. So I just wrote it that way. Is that clear? So in this diagram, what is this pole? I've spent so much time on that. What is this pole? I hear both. See, that's the thing, I hear both. What did I say? From this side, the current appears to be counterclockwise, and what's the letter? North pole. And from this side, the current appears to be clockwise, so it is the south pole. Expect a question on this. Okay, here is Biot and Savart's law. Two scientists. What you see on the screen now is a conductor. Try your best to understand. Is a conductor that is not of a particular shape, as you can see. And you can imagine that this conductor is divided into small, tiny pieces all along its length. And you just consider a very small length of this conductor. The length is dl. Can you see that? So this is called an elemental conductor. Just like element, small part of a conductor. It's a tiny piece of the conductor. What's the current flowing through it? I. Will it produce a magnetic field? Yes, all around it. And didn't I tell you that the magnetic field would be perpendicular to the plane containing the conductor and the point? So if you look at this, does it make sense? What's the direction of the magnetic field now? According to this, it's out. Is that okay? According to what we have studied, is that okay? Current flowing and the point is on this side, so it has to be. That agrees, right? Okay, so the magnetic field is outside. But according to Biot and Savart's law, the magnetic field, the small magnetic field, that's why it's dB, is given by mu naught by 4 pi I dl sine theta by r squared. But that can be written as I dl cross r by r squared. That's a cross product. How do you define a cross product? A cross B. A B sine theta. Okay, so you can either write it as a cross product or you can write it as the whole thing where you use the cross product. So you go dB is equal to mu naught by 4 pi I dl caps small. Okay, sine theta by r squared. Either way, it's the same thing. But what's theta? I'm sure you know all the other terms. What's I? The current flowing through the conductor. DL is the length. R is the distance of the point from the conductor where we want the magnetic field. But what's theta? Theta is the angle between the line joining the conductor to the point. What's that? Isn't this the line joining the conductor to the point? And the current. You see the two arrows, red and green? The angle is, that angle is theta. Could that angle be 90 degrees? Yes. If that is 90 degrees, then you know sine 90 is 1 and the magnetic field would be maximum. Clear? That is Biot and Savart's law. Okay. Yeah, I told you that the direction of the magnetic field is? Okay. Probably that's what I'm writing. Direction is perpendicular to the plane containing the conductor and the point. Not the current, and the point. And would it be out or in? Depends on what direction the current is flowing in. I've written that. Okay. Because a PowerPoint there from the textbook publisher has a lot of stuff and you don't know which is important. But here, just the important points. That should be clear enough. We're trying to find the magnetic field due to a circular loop. You know how the loop is kept as you look at the diagram, right? And we're looking at a point on the axis of the loop. Is that clear? That point is on the axis of the loop, and it is x distance away, right? Okay. Please listen very carefully. Now imagine that this loop is divided into a number of elemental conductors. And we're looking at a conductor right on top. Can you see that? So isn't this line joining that conductor to the point? And therefore the distance is r. Isn't that how we take the distance? All right. Now somebody has to be really intelligent and tell me what theta is in this case. Do not look at the board because it's misleading. What is our theta in the formula? Our theta is the angle between the current and the line joining the conductor to the point. Right? Okay, the current is flowing. The current is flowing this way, right? So on top, the current is this way, and the line joining is this way. What's the angle between the two? 90 degrees. Thank you for those who understood. It's 90 degrees. I'm not talking about the theta there. Okay. Therefore, what's the magnetic field? The magnetic field would be maximum, and that would be given by the formula dB is equal to mu naught by 4 pi I dl by r squared, isn't it? Just because theta is 90. Is that our dB now? Yes, sine 90 is 1. What's the direction of that dB? Hey, what's the direction of the magnetic field? Isn't it perpendicular to the plane containing the conductor and the point? It's 3D. Can you now tell me which the plane would be? Where's the conductor? Isn't the conductor here, the elemental conductor? Where's the point? Here, right? So, isn't this the plane? Isn't this the plane containing both? And shouldn't it be at right angles to that plane? Isn't that what you see? Well, if you can see. Do you see this? Okay, this is it's a line here, but I'm sure you understood. That's the plane containing the conductor and the point, so this is this way. On the exam, you will have derivations this time too. Okay, so that's the magnetic field. Agreed? Can't we resolve that into two components? One dBx, the other dBy. Okay, we're almost done. Now, let's consider an elemental conductor exactly opposite to the one that we considered before. Hello? Diametrically opposite. Now, can you tell me what the direction of the magnetic field would be? Wouldn't it be perpendicular to this plane? It's not shown in the diagram. Wouldn't it be this way? Come on. Couldn't that be resolved into dBx and dBy? And do you now see that the dBy's will cancel out? And so you only have the dBx's adding up. So to find the total magnetic field at this point, you just have to take integral dBx. That makes sense. Did that make sense? Okay, that's what I'm going to do. Integral dBx. You can try to get it on your own. Write dB, mu naught by 4 pi I dl by r squared. Integrate that. Go ahead, integrate that. Integral dB, sine theta. Theta is 90, remember? Wait a minute. This theta now, I would have almost made a mistake. According to this diagram, this is theta. If this is theta, come on. Okay. Therefore, dBy would be dB cos theta, right? And dBx would be dB. Therefore, you are taking integral dB sine theta. That make sense? Okay, dBx is dB sine theta. That's what I'm trying to say. So integral dB sine theta. And what's dB? Mu naught by 4 pi I dl by r squared. Sine theta. When you integrate, can't you take the constants out? What are the constants? Let's go before you see it on the screen. What are the constants? Mu naught by 4 pi. What about I? I is a constant for all conductors. What about R squared? It's constant. Isn't the distance from each conductor the same to that point because it's on the axis? Okay. So take all that out. What do you have? Integral dl, which is what? What is integral dl? Be careful. Don't just be mathematical purely. What's integral dl in this case? It's not. That's when you're purely mathematically do not think about the physics. It's the circumference. Thank you so much. Integral dl is 2 pi caps r. 2 pi caps r. What is caps r? Radius. Okay. I'm going to make two substitutions. One I've already told you. Before I show you the next substitution, somebody look at this right angle triangle, tell me what sine theta. Look at this right angle triangle, please. Tell me what sine theta. Sine theta. Sine theta. You know, I'm struggling to get a sine theta. Okay, caps r divided by a small r. Struggling to get a sine theta. Okay, so I'm making two substitutions now. Maybe one by one. First I make that, then. But you will see both the substitutions coming up. And that will be the final formula. Did I say sine theta is caps r by small r? Yes. And what's integral dl? Okay. Cancel whatever you can. And you see the r cube there? Do you see the r cube coming up? And from that right angle triangle, can't you say that small r squared is equal to caps r squared plus x squared? Come on. In a right angle triangle, hypotenuse squared is equal to sum of the squares on the two sides. Therefore, what would r cube be? What would r cube be? Okay, what's r squared? From that right angle triangle. Right? So my question is, what's r cube then?
Wait, R cube is that.
Thank you. R squared plus x squared raised to 3 by 2. Go get your math. Because r squared is r squared plus x squared, r would be square root of that. Square root is just raised to half, isn't it? And then I have to raise it to 3, so it will be 3 by 2. Okay. That's what I'm going to do next. I r squared by 2 times r squared plus x squared. Or raised to 3 by 2. I'll let that run. See, for those who did not understand, remember that at the center x is 0, the top is r squared, the bottom would be r cube. That's why one of the r's will remain. That's why you get mu naught I by 2r. And also write, though I have not included it, please write if there are n turns. If there are n turns, then the formula becomes mu naught ni by 2 pi r. Is that making sense?
And as